Let's take a look at another example. It's based on the puzzle developed over a century ago. According to the legend, monks in a remote monastery could predict when the world would end. They had a set of 3 diamond needles. Here is a modern setup of the Tower of Hanoi. Here we have 3 wooden needles instead of diamond needles. Stacked on the first diamond needle were 64 discs of decreasing size. Here we have only 8 discs. The task is to move all the discs from one needle to another by following certain rules. According to the legend, the world would end when they finished the task. The monks can only move one disc to another needle each day. Perhaps these are very heavy discs. Here are the rules that they have to follow when they move the discs. Only one disc could be moved at a time. It would have been easy if they could move the entire stack of 64 discs to the destination in just one move, but that was not allowed. A larger disc must never be stacked above a smaller one. Otherwise, they could have just moved the discs one by one from the top of the source to the destination. This way, the world would end in 64 days. Lastly, only one extra needle could be used for intermediate placement of discs. Otherwise, they could have spread all 64 discs on the ground and then moved them to the destination. This would have taken 128 days for the world to end. By following these rules, these seemingly simple tasks would require 2 to the 64th power minus 1 moves. But how long would this take to end the world? You may not believe it, but 2 to the 64th power is an enormous number. Even if we speed up the task by moving each disc every second instead of every day, it would require 580 billion years to complete the task. Perhaps the legend has some truth to it. No one would know how the world would be like 5 billion years from now, but it would surely be a very different world. In general, for n discs, the number of steps required would be 2 to the n power minus 1. Let's look at how the problem could be solved using a program. Let's first take a look at a few simple examples. This diagram shows the start state for the case with 3 discs, and the task is to move them from the source needle to the destination with an auxiliary needle that could be used for temporary placement of the discs. This is the goal state, but we have to follow the rules that we described earlier. For example, we can't move the whole power of this all at once to the destination. Let's look at a simpler case with just 2 discs. The case with just 1 disc is too straightforward because you can just move the only disc from the source to destination. This shows the start state for n equal to 2. The goal is to move the 2 discs from A to C. You cannot simply move the smaller disc from A to C and then the larger disc from A to C because you would then have a larger disc on top of a smaller one. The smaller disc is first moved to B. This would be the intermediate result. Now A is freed up and it can be moved from A to C. The disc on B can now be moved from B to C. And we achieve our goal in 3 steps. As I mentioned earlier, the required number of steps is 2 to the n power minus 1. In this case, n is 2, so 2 squared is 4. 4 minus 1 gives 3, same as the number of steps we found here. Let's go back to the 3 disc problem. Here is the start state. We have just solved the 2 disc problem, so we know how to deal with n equal to 2. And we know that in order to move the largest disc, or bottom disc from A to C, we must first free it up by moving the 2 discs above with somewhere else. Let's assume that the 2 smaller discs have been moved to B, but we don't need to pay attention to the detailed steps because we already know that it could be done in 3 steps. Once the largest disc is freed up, it can be moved from A to C. A is now at its final destination, and we don't need to move it again. The remaining job to be done is to move the 2 discs from B to C. Again, we know how to solve the 2 disc problem in 3 steps, so we can skip the details. Notice that one difference here in this step is that B becomes the source needle and A is used as an auxiliary, while C is still the destination. As illustrated in this diagram, the solution can be achieved in 7 steps. Again, for n equals 3, 2 to the 3rd power is 8. 8 minus 1 gives 7. Here is a diagram that illustrates the idea of an algorithm for solving the problem using a method called towers with 4 parameters. We start solving the problem by specifying the size of the problem, in this case 3, and then A is the source, C is the destination, and B is the auxiliary. To solve this problem for n equals 3, it will invoke towers for a smaller problem with n equals 2. In this case, A is the source, B is the destination, and C the auxiliary. Here are the rest of the steps for this called the towers. This step here is to move the largest disc from A to C, which requires just one simple step. This called the towers will complete the task by moving 2 discs from B to C using A as auxiliary. Notice that the 2 calls to towers here are recursive calls, as well as other calls to towers below. And step 4 is a non-recursive step, as well as steps 1, 2, 3, 5, 6, and 7. Hope that you can already see a pattern here. To solve the Tower of Hanoi problem for any given n, we can first move the n-1 disk on top of the largest disk to an auxiliary needle by following a sequence of steps using a recursive call. In this call, A is the source, B the destination, and C as auxiliary. Then move the largest disk to the destination using a non-recursive step. Finally, move the n-1 disk from the auxiliary to the final destination using another recursive call. It is important to notice that in this call, the move of n-1 disk is from B as the source to C as the destination using A as the auxiliary. Once we work out the strategy, the implementation of the recursive method for solving the Tower of Hanoi problem is quite straightforward. Here is the definition of the recursive method towers. In this implementation, instead of using 4 parameters, only 3 parameters are listed here. Num is the number of disks, from is the source, and to is the destination. We don't need the 4th parameter because it can be determined inside the method. Assuming that the needles are labeled 1, 2, and 3, this statement here is where the location of the auxiliary needle is determined. Actually, the way it's done is quite clever. You may want to think about how this works. I'll come back to this later. This part is the non-recursive call when num equal to 1, or there's only one disk. Inside the else part, the 3 statements here represent the 3 branches that we have just seen when describing the solution. The 3 red arrows correspond to the 3 statements that we have just seen in the body of else, including 2 recursive calls to tower and a non-recursive step. The first recursive call is for moving num-1 disk from the location from to the location temp. The second statement is to actually move the disk on top of the from needle to the destination needle. The third statement is a recursive call to move num-1 disk from the location temp to the location to. Have you figured out why the label of the auxiliary needle temp can be determined using the expression here? Assuming that the needles are labeled as 1, 2, and 3, 1, 2, and 3 would add up to 6. Once 2 of the 3 numbers are fixed, we can determine the third by subtracting the values of the 2 known numbers. In this case, from and to from 6. For example, if from has a value of 1 and to a value of 3, subtracting 1 and 3 from 6 would give 2, that is, the third label. So this is the entire implementation of the Tower of Hanoi solution. Although it could take 580 billion years to solve the problem, the program itself is very simple. Let's take a look at the program in BlueJ.